now. Okay, all good. So hello and welcome everyone again to our School of Computer Science Bachelor Seminar Series. So today we have a special speaker from National University of Singapore. And for those who are new and joining us from other universities, I would like to say a couple of words about the Bachelor Seminar Series. So we named this seminar series after Sir Adolph Vassar, who enabled the University of Sydney to build its first computer, and then eventually helped us to form our school, which was the first computer science school at, in Australia. At some point, our school even, graduates from our school were called, Vassar graduates as well. So with that, I would like to introduce our speaker. And our colleague, Dr. Anusha Vitana, is the one who invited our speaker to do this Bachelor Seminar Series. So therefore, I think it's more appropriate I ask Anusha to introduce our speaker today.
Thank you very much, Kanchana. It is my great pleasure to introduce Professor Shengdong Zhao, and very excited about this talk on heads-up computing. Shen is an associate professor of the computer science department at the National University of Singapore, where he founded the NUS SydCHI lab. I first got to know Shen when I was an associate chair in the ACM CHI conference, where Shen was one of the program chairs, I think both in 2019 and 2020. And for those who doesn't know about CHI, it is the top venue in SydCHI. So get to the program committee chair, you have to do some very impactful work, and Shen continues to do so. Shen did his PhD at the University of Toronto and has a master's from the University of California, Berkeley. I can go on and on about his various accolades, but I think we are all here to listen to Shen talk rather than I talk about him. So I will hand over to Shen, and thank you once again for doing the talk.
Thank you, Anushu, for the introduction, and thank you for inviting me for coming to this talk and provide a chance to share some of my thoughts with my academic colleagues. And also thanks, Kanchana, for the introduction as well. This is my great pleasure to present you some of my latest thoughts about what we should do for the future and what will be the next interaction paradigm will be like. So what actually triggers me to think about this particular question? Let's zoom back a little bit and touch on to the topic of humans co-evolution with tools. One of the big difference between human and some other species in the planet is that we have the ability to use tools and thus make us be able to create a lot of innovative things to improve our lives. But if you look at this kind of highly contracted view of how humans evolve without tools, you can see that on one hand, the tools made us much more powerful, be able to accomplish a lot more, but you can also see that the tools also have some other impact in our lives and maybe not so positive. And you can see that this has ascending trend, and there's a descending trend in this particular graph. So the aspects that may be a little bit kind of controversy here is the topic related to technology and the quality of our lives. We all know that technologies improve many aspects of our quality of lives. But perhaps if we think about a particular aspect, let's say the work-life balance, right? So if we look back in history, looking back in the time as we are currently, most of us are knowledge workers, and go back a little bit time, we go to the factory workers and back to farmers. And finally, we move into our ancestor who is living as a hunter-gatherer. The question here is, do we actually improve our work-life balance or improve the quality of our working conditions here? And which role has the best work-life balance? Right? I think, if you can think about this question in a different angle, if you want to buy a ticket for a holiday to one of these times, right? Which days will you buy a ticket to if you can time travel and play the role of the people around that time? Actually, I did this kind of survey informally with many other people, and very interestingly, many people mentioned that hunter-gatherer time is one of the more interesting time for them they wanted to get into. And people in that particular society may actually have a better work-life balance than today's people. So why is that so, right? We all know that technology makes us much more advanced. But if you're looking into this issue a little bit more deeply, you find that there might be an interesting trade-off between the advancement of our society, right, in which technology enables us to evolve from very simple society to very complex societies and make us from maybe weaker in terms of our power to much more powerful forces that can conquer many problems in nature. But when we look at individual lives, right, it actually makes us somewhat less powerful. Or if you look at the kind of all-aroundness that we have, we are much more specialized today as compared to before. Imagine you are a hunter-gatherer, right? You have to use all of your capabilities, your smell, your taste abilities, your memory, your navigation skills, your muscle have to be strong, right? You have to be very mobile. And a lot of our capabilities are fully developed because of the needs of the hunter-gatherer stage. But moving into the modern stage, we use much less of our capabilities, and we develop into very specialized things. And many of us just sitting in front of a computer 8 hours a day, right? And in terms of freedom, if you talk about the times that we're in hunter-gatherers, we move around a lot. Like every day we move maybe 10 kilometers or more. We like, try all kinds of different foods, explore nature, and many, many different things. But when we go down to our modern life here, we are much more constrained to our office environment or the specialized environment designed to make us work more specialized and efficient. So these aspects, we can clearly see that it's actually going downwards in some ways. So let's kind of look this a little bit in terms of the abilities or the kind of the powers that we utilize when we had before and now, do a more contrast. If you are a hunter-gatherer, you have to use all of your capabilities in some ways: body function, the hearing, the hand, the mobility, the vision, and many, many things that you just have to be very all-rounded to be able to do well in that society. But when we move on to the modern world, like in today, you realize that somehow the technology have made us into these creatures that only mostly use our eyes and our hands. And even the hands is not a complete use of our hands, but only the tip of our fingertips, right? The touch points. So this can be a little bit undesirable. And the talk is ask us to think about this question again, and perhaps in the future, when we actually develop our new working environment, can we somehow reverse this trend, right? Make us more all-rounded again, and also make us much less constrained. So that kind of points out one particular vision or the desirable outcome I hope to get from having this new interaction paradigms, right? the current situation when we are working, right? We are working in a constrained setting, typically, in front of a computer, very specified. You're sitting there for a long time, and because of that, you cannot really engage in many of the other activities while you're working. And then this kind of lifestyle is unhealthy, and sometimes it can be quite painful, right? What we hope to actually achieve in the future is that the work can be done anywhere, right? And it is in harmony with our other life activities, and our working style is actually healthy and much more enjoyable for us to actually experience. So, but now let's ask a question. So what prevents us from having such kind of working life, right? What prevents us that? If we look at current situation, it's undesirable, but why we are in it? So we can kind of look back on what we just talked about, the human co-evolution with tools. Humans invent our tools, right, to change the world. But the tools actually come back on us and shape our lives in certain ways. And sometimes we become, without notice, the slave of tools. So this can be very apparent viewing from this particular figure here. As we invent our computers, our laptops, mobile phones, we all have to adapt our behaviors to suit the needs of the computer, and then that creates undesirable consequences. So the talk is about, let's think about some new tools, right, and the new interaction paradigms that can potentially enable a much better work-life balance, a much better way of working in the future. And so to do that, as we offer on the user-centered design, we know that we need to first study what are the problems of existing tools before we can think about solutions to overcome them. So what are some of the problems? Well, one of the problems of existing tools is that the devices are designed in what we call a device-centered approach, right? All the input and output capabilities is centered on one piece of artifact, right? As a result, you can see that humans have to adapt their posture to suit the needs of the device, right? We have to just all cater to this little center thing and bending our body just to make sure that we can, assess that. This is a little bit undesirable. And the second issue of the current tools is that the current tool heavily relies on our eyes and our hands, which is also something we also use a lot in our daily tasks. And this means that if we want to do some computing tasks, we are not allowed to do our daily tasks at the same time, and they have a conflict. This is, again, somewhat undesirable. And the third issue of the current tools is that they are very attention demanding, right? They requires often dedicated attention to operate it, so that it becomes less easy to incorporate them or blend them into our daily lives. Okay. So with these problems in mind, we try to come up with a new paradigm, what we call heads-up computing. So the goal of heads-up computing is to be able to offer a more seamless, just-in-time, and intelligent computer support for humans while they are doing their daily activities. And the approach we are taking is, first, we want to redesign the hardware platform so that they matches our human input-output capabilities. So we use what we call a human-centered design instead of device-centered design. And the component of the hardware will consist of headpiece, handpiece, and potentially a body piece. And we also want to change the way we interact with computers from what we're currently doing, the keyboard, mouse, or touch display based, to voice plus eye tracking plus subtle hand finger gestures for input. And then we use, hopefully, our optical head-mounted displays and multimodal feedback for our output. And finally, we want to enable and facilitate a kind of resource-aware interaction, where interaction is based on our available resources, which is synergetic to our current activities. So let me just play a quick video about what this vision is about, and then we will dive into some of these features in more details. The lab's vision is on what we call the heads-up computing. It's an interaction paradigm that focuses on living instead of interacting with devices. And it adopts what we call the human-centric design. So the device fits the human's needs, human's design. Instead of the traditional approach where you put input and output all in one piece of device, a human have to change their posture and change their way of interaction to cater to the device. With this new heads-up computing design, human now can engage in a variety of activities and still receive seamless help from devices. A lot of our natural activities that we want to engage in, such as running, cooking, socializing with friends, also requires our visual and manual movement. This causes a conflict. But with heads-up computing, we try to utilize voice, subtle gestures as a means to interact. And with the distributed design, we can allow people to actually interact with computers, receiving information without disrupting their current activities. And we call this a synergistic interaction. Existing interaction paradigms mostly are reactive in nature. What it means is that they only respond to humans' requests but we want the future interaction paradigm to be more proactive so that it can anticipate the human's needs and provide just-in-time help without too much human's involvement. This naturally facilitates a balanced, healthy living.
We wanted to change the interaction paradigms in a sense to utilize more of our body and to maximize the human potential. This can be done through the replacing the traditional hand interaction and with the gesture interactions.
So I think the vision of the lab is more to facilitate on-the-go interaction. So that's where iEditor comes in. And then, as the name suggests, it's a text editor in front of your eyes in the near eye display. So we implemented the near eye display with see-through smart glasses, which is Physics Blade, and how you can edit the text on the text editor on the smart glasses is by using your voice. And there's also a secondary form of input, which is this wearable ring mouse. And with this, you can do any selection or navigation tasks to aid your voice-based correction on the smart glasses.
Okay, so I hope this gives you a kind of an overview about what our vision is about. You probably see similar versions, or maybe from some earlier videos where people projecting live, where people use augmented reality. But heads-up computing differs from the previous approaches that we trying to think about exactly what are the mechanisms that can actually help you to realize these goals. So let me just dive into some of the design features and approaches in more details. Okay, the first one is we are trying to use what we call human-centered design versus device-centered design. And I think you already kind of see that. I explained earlier that because of all the input and output capabilities are on one device, right? So that's why it forced the device to adopt this device-centered design where humans have to work along with them. What we want to do is we want to match the input and output of the devices to the input output of a human. Right? In this way, human can more freely doing what they want to do while engaging in other activities. So, well, people are saying that, okay, is that just wearables? Actually, it's not, right? There's many wearable devices have been developed, but they are not necessarily adopting what we call a human-centered design. For example, if you look at this Apple Watch, right? Apple Watch, if you want to interact with that, sometimes you have to just, like hold a hand up, and then you have to do a lot of touch gestures with the device itself. That's not human-centered. That's not human-centered design. Human-centered design, it should be that we should keep our current posture as much as we can and do the activities we want to do. But in this case, you actually still have to engage very much on the device and then kind of interact with that. It's actually just another way of what we call device-centered design. It's not a human-centered design. And then people have been envisioning maybe enlarging the display area on your arms, or even kind of completely block your eyes with those virtual reality devices. To us, those are also not human-centered design. The one with arm is just make the display a bit bigger, but it didn't change the nature that you have to change your postures a lot to interact with the device. The one with the kind of heads-up display that completely block your vision is something, again, against our principles, because we want the new interaction paradigm to enable us to live better, to connect with more people, to engage more into the natural activities. We don't want you to isolate yourself into a virtual world. So that's not, again, not what we want. The last case here, right, you can see the Google Glasses. It has the nice output channel here, which allows you to see information while still be able to attend to the environment. But the input in terms of gestures, I don't think that's the right approach. Right? I think we should redesign that so that the input doesn't have to do in this unnatural way. So what do we propose here? We propose that we try to come up with what we call a headpiece, handpiece, and potentially a body piece. This is inspired by our understanding of our body capabilities. Right? If you look at our sensors in our human. You can see that there are 3 hot zones, right? The 3 hot zones are our head, which is concentrated with a lot of our sensors and some of our actuators. And our hand is the main actuator and also our sensor for haptics. And finally, our body, right? So those are the 3 hot zones which, our body is designed and evolved over the years to develop. So I think it would be nice to be able to develop a device that matches these hot zones. So we start with what we call the headpiece and handpiece right here. The second, we need to change the way we interact, right? The current way of interaction is first of all, it's resource conflicting, and also it's attention grabbing. So can we change it in something that we are more accustomed with? For example, right now I'm talking to you guys with voice, right? Voice is a very important communication channel for us to deliver information, and it's quite efficient as well. Why not rely on voice more, right? And also, when we receive information, we naturally move our eyes. Can we utilize our eye tracking to do that if we have glasses which can equip with eye tracking equipments for that? And then, of course, those two are not enough. We need some kind of gesture or finger and manual controls. So, but we try to use them as in a subtle way, which hopefully not to conflict with our existing activities. So we need to have the support of subtle hand finger gestures. And for the output, we can think about multimodal output and as well as the head-mounted displays. Right. So this is the insight from that is that our daily activities are very hands and eyes busy, right? And if you also make the human-computer interaction task hands and eyes busy, that will cause a lot of conflict. So let's try to use other modalities so that it's more complementary to our daily activities. And at last, we have to think about to design interaction in a different way, right? Currently, I think a lot of our interaction designed with the assumption that people have dedicated attention to do that. But if we want to support people's daily activities more, user will not have their dedicated attention and not even the whole capabilities available. So we need to think about that interaction designed with that in mind. So if we look at the human resources or the vision, hearing, or the capabilities we have, right? Some of them will be utilized by our current activities. Some will be limited by our environmental constraints. So it will be, if we can try to design the interface and interaction based on what's left, and then be aware of what's available and do what we call resource-aware interactions, that will be something that allow us to create a much more harmonious blend between technology and human daily lives. So yes, of course, the vision is exciting, right? I mean, different from some of the more scientific vision that you see on YouTube, right? This one, we actually try to work on it. When you're working at it, you will find out that it actually has a lot of different challenges. So first one is hardware design, right? What kind of hardware do you want to use? So this is our initial design. Right? We have what we call headpiece, which is smart glasses, right? And then the smart glasses, hopefully will eventually provide real-time visual and auditory feedback. And hopefully it can understand what humans sees and hears, and understand humans' facial gesture and emotion, understand our attention, and then be able to process speech input, right? Then we also have some kind of handpiece, which provides some kind of real-time haptic feedback, and then can allow us to input gesture and hopefully text input. Okay, so I think the kind of this eyeglasses seems to be less controversial, right? People will think that, okay, yeah, if we want to receive feedback next to our eyes, eyeglasses seems like an obvious solution. But the handpiece here is still a little bit more room to design in what way we can do it. So we actually carry out a study and then try to compare the different type of subtle gestures, and then try to find out which ways is what we call a more optimal ways to allow users to provide their subtle gestures. So let me just play this video. This is a paper published at Mobile HCI.
Hello, my name is Shardul, and I'll be presenting our recent work from the NUS HCI lab, done alongside Ashwin Ram and Shengdong Zhao on ubiquitous interactions for heads-up computing. Currently, most optical head-mounted displays, or OHMDs, allow users to interact with them using handheld controllers, trackpads on spectacle frames, or voice input. But these modes of input could be uncomfortable if used frequently, unsuitable when the hands are busy, or even inappropriate in certain contexts. A research direction on subtle interaction technique focuses on designing interactions that are more comfortable and less disruptive to users and to those around them. Examples include foot-based interaction, hand gestures, or gestures using jaw-teeth movements. So subtle interaction techniques could be a viable alternative to provide input to smart glasses. But there are also some practical considerations which might make their long-term use more challenging. For example, it'll be hard to tap your foot when you're walking, or to use jaw-teeth when you're chewing or talking. So in order for OHMDs to satisfy users' informational needs as they're going about their daily life, it is important to design interaction techniques that are suitable across everyday scenarios. So the question that is driving our research is, can we find interaction techniques that are synergistic to people's everyday activities? And in order to answer that question, we first compare different subtle interaction techniques, and in doing so, answer a series of questions on how do we even evaluate the subtlety of an interaction technique, or how do we pick representative contexts in which we could compare them in. Second, by comparing different subtle interaction techniques, we were able to revisit some of the trade-offs and appropriate use cases of these subtle interaction techniques when providing input to smart glasses. Third, we found that thumb index finger interaction was the most preferred cross-scenario subtle interaction technique. So we conduct a follow-up study to come up with design recommendations for using thumb index finger interaction to provide input to smart glasses for long-term use. In our first experiment, we conduct a Wizard of Oz study where we compare 4 subtle interaction techniques in 3 representative contexts. These subtle interaction techniques were based on the characterization and survey of papers by Pohl et al. The 4 subtle interaction techniques include jaw-teeth, arm, foot, and thumb index finger-based interactions. In terms of the representative context, as you can see on the video on the left, the first one is carrying bags and walking, and as soon as the person sees notification on the smart glasses, they tap their feet to provide input. The video in the middle shows the second context, which is folding clothes, and the one on the right shows the third context, which is giving a presentation while holding an iPad. From this experiment, 2 results stood out to us. First, that in terms of task completion time, thumb index finger interaction was 1.2 times quicker than other modes of interaction across these 3 contexts. Second, 87.5% of the participants preferred thumb index finger interaction technique compared to others. These results suggest that thumb index finger interaction could be the cross-scenario subtle interaction technique to provide input to smart glasses. In order to validate that result, we conduct an in-the-wild experiment, this time to evaluate thumb index finger interaction technique in the form factor of a ring mouse. Participants provided ratings for comfort, disruptiveness, and how socially awkward they felt when performing this interaction. And we were able to better understand some of the limitations and challenges associated with thumb index finger interaction technique and the form factor of the ring mouse. Participants found it harder to perform activities that also involved the use of thumb and index finger, like cutting and holding a doorknob. The bulky nature of the ring mouse also made it harder to do activities like writing or painting. So in order to support thumb index finger interaction for long-term use, the device must be lightweight, waterproof, provide firm grip, and accommodate discrete and comfortable gestures. In conclusion, in this paper we evaluate the subtlety of different interaction techniques for OHMDs and we find that although each interaction technique has its relative advantage, thumb index finger interaction, contrary to expectations on designing systems for hands-busy tasks, was the most preferred as a cross-scenario input technique for smart glasses. We also provide insights for future research on interactions that are synergistic to people's everyday activities for a wider adoption of smart glasses. Thank you for listening.
I hope this talk gives you a sense of why do we choose the ring mouse as the handpiece for currently. Of course, I think in the future, we can design better handpieces to accommodate some more needs that's needed. But we do find that using some index finger gestures, it is the best cross-scenario interaction techniques for subtle interactions.
Hello, my name.
So the second question we have is, how do you support ubiquitous information processing, right? I can imagine the future workers are mostly knowledge workers as well. So we want to support the lifestyle and the way that they can process knowledge while they are in, let's say, on the beach, working in the forest, or in any other situations. So it's very important to support what we call information processing on the go. And for that, we introduced Editor, which you briefly learned about. And here I'll just play a video to introduce a bit more. This is a Kai paper.
We text while walking all the time. For that, we enter and edit the text using our phones. Our phones are awesome, but they keep our hands busy and our heads down. We propose Editor, a heads-up smart glass-based solution to on-the-go text editing.
In order to,
the user sees the text on a see-through smart glass and can correct the text using voice input. A speech recognizer transcribes the user's speech to text and sends the user utterance to a processing unit. Additionally, the user uses a hand controller for text navigation and selection. The speech and the controller comprise the input interface of Editor. The processing unit changes the text based on the user input and pushes the changed text to the app UI of Editor running on the smart glass. The system also gives audio feedback of text change confirmations and errors. Let's see how the system works with voice and controller input. Our system shows the text sentence by sentence. Instead of having to remember commands, users can correct the text by re-speaking, that is, by speaking over erroneous parts of the text in order to correct it.
dog, domestic animal. It is always faithful. Human beings.
Users can scroll through the text by swiping right or left on the controller trackpad. For finer grain control over the text, users can enter a select to edit mode by pressing the left button and select words by swiping on the trackpad. The selected text can be changed by speaking
dogs, friendly.
To initiate a range selection, user has to press the center button. Swiping on the trackpad adds or removes words from the existing selection.
Playing.
Selected text can be deleted either by long pressing the center button or by saying the delete keyword. To insert new content, users use the top or down keys to first place the cursor before or after selection and then speak.
On.
Pressing the left button takes the user out of the select to edit mode. Changes can be undone with a short press and redone with a long press of the right button. Participants use the two techniques in a counterbalanced order for making both simple and complex corrections in the text, while working on 3 different path types. These are sample texts that the participants corrected during the experiment. Participants see the text sentence by sentence. At the start of the experiment, we asked each participant to walk a 20-meter segment of each path at their normal walking speed 2 times. We used this measure to compute how much they slowed down from their normal walking speed while performing the experimental tasks using the phone or our proposed technique. These are snippets of the actual paths that the participants walked on. Our study showed significant performance benefits of our proposed technique over the phone when either the path or task difficulty increased. Thus, our paper rethinks the status quo of text interaction on the go.
Okay, I saw a couple questions in the chat. Maybe I'll address those questions first before we move on. So there's a question from Tillman said, I would be interested in your thoughts about removing technology by using tech to build inherent human skills rather than technological augmentation. Rather trivial activities, cellular preparation or navigation could be easily learned rather than having users rely on technology. Such removal will also play into our argument that people long for simple lives with real experience. Yes, that's a very good point. Definitely, maybe the example we show in the video is a little bit too simplistic. Probably for doing salad and other things, right? We can probably do it ourselves. That might be a better way of doing that. But imagine that you are trying to learn to build an Arduino component, or if you are trying to, do some aircraft engineering, right? Those tasks, it requires years of training before you can actually get engaged with. If with heads-up computings, we can potentially allow people learning them much quicker, and then performing those tasks, with a much easier experience as compared to what we have right now. So it is human sometimes need help, sometimes they don't need to. Right? So you can still have the control on what that you want the computer to help you with. And when you do want the computer to help with, we want the help to be seamless and not disruptive to your current activities. Okay, so there's another question a little bit top by Lindsay. So that you mentioned that the user can use the device without being interrupted in their daily activities. So I see how this device enables us to not have to change our posture and hence not interrupt our activity in that way. Could one argue that receiving a mail in front of your eyes during an activity is also a form of interruption of the activity caused by the device? Yes, that's definitely an interruption. So that's why we want to introduce what we call resource-aware interaction. The device should be more aware of human status and their current activities. For example, you don't want to be interrupted in a meeting, right? If the device knows you are in a meeting, it will hold on the delivery of the message to you. Or if it is an emergency message, it will be delivered in a way that does not distract you too much from the meeting, right? And later on, we will show some of our work, which explains how we do that. Okay. So that's another question. Okay, and then there's another question. Okay, yeah. Okay, so it seems like these are the two questions. And thank you, Truman, for your question. And then let's move on to the next slide. So we come up with our initial design of how to do information processing. But of course, that's just the initial work. I believe the alternate form will still be evolved and hopefully optimized as we go along. So now we talk about the kind of the word processing, text processing in the wild. Another question we have is, how do you present information to the user while they are engaging in daily activities with minimal interruption, which this directly hopefully addresses Lindsay's question earlier. So for this one, we will present the work we did for Ubicom in 2021. And then it hopefully can explain some of the principles behind this approach.
Hi, my name is Ashwin Ram, and I am from the NUS SydCHI lab in the National University of Singapore. I am pleased to present our recent work which explores the use of optical head-mounted displays for video learning on the go. Today, we perform a wide variety of tasks that require us to access information on the go, be it texting or even watching videos. Recent studies suggest that this is also the case with learning, with many users adopting mobile learning. Current explorations of mobile learning, however, have largely focused on language learning tasks that rely on static pictures and text. But with the popularity and benefits of online learning videos and MOOCs, we ask whether it's possible to view and learn using more dynamic content such as videos on the go. Prior investigations using smartphones or iPods for on-the-go video learning found it to be quite difficult, mainly because our attention is divided between learning and the environment. How then can we support video learning on the go? To better understand the situation, we interviewed and surveyed users, asking them about their motivation to watch videos on the go and the difficulties they face doing so. We found that in on-the-go situations, many users did not use their smartphones for visually demanding tasks. However, a significant number of users had personal needs or goals, such as learning for an upcoming test, which motivated them to continue their learning on the go. But users mentioned that using smartphones to do this decreased their situational awareness, as they had to maintain a heads-down posture and frequently shift their attention between the display and surroundings. To overcome some of these shortcomings of smartphones, we consider the emergent optical head-mounted display platform, which can be used in a heads-up manner and has a see-through display. These benefits make OHMDs a potential alternative platform for on-the-go video learning. Yet, viewing digital content alongside the environment in OHMDs can also distract users, making it harder to focus on the video. Existing videos may not suit the OHMD platform as they require focused attention. Hence, we investigated how video content should be presented on OHMDs. We found that a new presentation style is required for on-the-go acquisition of dynamic information on OHMDs, called LSVP, which stands for Layered Serial Visual Presentation. Let's take a look at a short clip which demonstrates what LSVP is and why it is better for video learning on the go.
Or we see actual lungs in a human being is that the left lung is shaped differently and it even has less lobes.
We found that by using LSVP on OHMDs, we were able to achieve better learning without compromising on users' walking speed as compared to using smartphones. So how was LSVP created? Well, we started by investigating 3 potential techniques that can help balance users' learning and walking using OHMDs. The first technique is highlighting, which varies the salience of an object to guide users' attention to it. The second technique is sequentiality. This also directs users' attention, but here it is the sudden appearance of the object which guides it. The last technique is data persistence, where the information that appears on screen is maintained throughout the video. This can help reduce the temporal load on users' working memory. We incorporated these techniques into real educational videos and tested it on an Epson BT300 OHMD by asking users to learn from the video while walking on a straight path. We found that data persistence and sequentiality are important for presenting information on the go, and combining both can improve recall, recognition, and walking speed of users. Finally, we compared this new design with the traditional one on 2 mobile platforms, that is, smartphones and OHMDs, to understand how the platforms compare in enabling on-the-go learning. We also considered 3 different mobility scenarios that users have to walk on: a simple straight path, a slightly more difficult curved path with obstacles, and a highly challenging navigation task which required users to walk by following direction boards. We found that users' immediate and 7-day delayed learning scores improved when using LSVP-based videos on OHMDs than with phones. This could be because users are able to switch their attention more efficiently using OHMDs And the LSVP design complements this by guiding users' attention and reducing the impact in case users miss information. It also improved users' walking speed in the more difficult navigation scenario. This work serves as one of the first steps in our ambitious vision towards heads-up computing. As a more human-centered approach, heads-up computing aims to seamlessly blend our computing needs with our daily activities. Crucially, it aims to support this using intuitive interactions that match our natural movements. However, there is much left to explore in the LSVP, including testing to see if the results extend to outdoor settings. Additionally, while data persistence is crucial, it can lead to clutter for longer videos, and this needs to be further investigated. Thank you.
So this is one approach that we can help to reduce the interruption that you get from multitasking in the mobile environment. So here, second video here is our recent CHI paper, which will appear later this year, which kind of more directly answers this question. What if during a conversation, during a meeting, some notification comes? How can I present that information with minimum interruption to the current setting?
Optical see-through head-mounted displays, or smart glasses, allow just-in-time information assistance anywhere at any time. However, receiving secondary information while engaging in a face-to-face conversation can interrupt social interactions. We propose a visualization technique that projects secondary information, such as reminder notifications, on the paracentral and near peripheral region of the eye. This allows users to read notifications while continuing to focus on their conversational partner.
The idea is fairly simple. Our eyes have different regions. We can leave the focal vision on what we call the conversation target, or the focus of attention, and try to present information on the paracentral and near peripheral area of the eyes in a kind of a circular fashion. And then this information can be simultaneously perceived while the user is still maintaining their eye contact, as well as some attention with their conversation partners. So this is one way to mitigate the interruption effect. And our experiment has shown that it can successfully do so. So these are some of the techniques that we are investigating. We're also looking into scenarios in which heads-up computing can help us to become a better information worker in the wild. So here is one potential scenario.
We present in-situ voice-based multimedia authoring workflow, which transforms traditional out-of-context experience writing to be enabled in context with ease. We reshape traditional multimedia content creation as a combination of voice-based input and photo-video taking to enable in-context content creation seamlessly. This enables easy in-context creation of experience snippet during the experience with minimal disruption, including all related contextual information such as pictures, videos, location, day and time, and so on. After the experience, the stack of live authored multimedia snippets can be edited and organized from a pre-generated draft with ease on memory recall. Please see our papers for full details.
All right, so maybe that's not enough context here. So imagine you are a blogger, you wanted to document your experiences, and you are in the wild. Instead of the current way, you usually go back home and then write down everything. We allow you to do live authoring, use voice, and using the camera that you have, potentially in your smart glasses. And then the device has all these contextual information about the location, temperature and all that kind of stuff. And then they can automatically draft a snippet of information for you as you go through your experiences. And then these information can be aggregated later on for you to do just a light edit for you to be able to publish those content with. So this is a kind of a snippet or a kind of a preview of a potential information worker will do, right? We can write papers while we are just outside, getting ideas, gathering things around, and we can talk to our devices to get some of the ideas out, and there will be support of feedbacks and to allow us to do this smoothly. And then we can minimize the time we really spend in our office. Okay, so for the sake of time, I think I was kind of stop right here. We barely scratched the surface in terms of heads-up computing here. So this is kind of a proposed kind of roadmap of the research that we hope to tap into. But this is an ambitious goal. I can definitely see that hopefully more people will be intrigued by this vision and work towards enabling that. And one note I just want to mention that what is the difference between heads-up computing and ubiquitous computing, right? Some people ask me that question. Okay, so if you look at heads-up or ubiquitous computing says that computing is made to appear anytime and everywhere, right? Computing can occur using any devices in any format, can exist in many different forms, including laptop, tablet, smartphones, refrigerator, or even a pair of glasses. So in other words, if you really look at that definition, ubiquitous computation is everything smart minus desktop computing, right? This is a little bit cheating in a way that they kind of say that, okay, anything beyond desktop is ubiquitous computing, which is great. And if you use that definition, definitely heads-up computing is part of ubiquitous computing, but that definition is too broad. And if it's too broad, then it loses somewhat its designing powers and loses its guiding powers here. On the other hand, heads-up computing is a much more specific, right? Its platform is defined by the head piece, hand piece, and potentially a body piece. And we only worry about one person's perceptual space, right? We don't really care about other parts. And our approach is using multimodal and resource-aware interaction. So we are much more specific. So using analogy, you can think about ubiquitous computing as this huge department store which has everything, right? But heads-up computing is this minimalistic approach that's designed for the essential needs of human to live in this kind of lifestyle. And you can also see that, ubiquitous computing includes every kind of devices, but heads-up computing is what we only care about, some of the wearables which associate with the human. Heads-up computing is a huge vision, as I mentioned earlier. Many pieces of technology and disciplines can contribute to it, including AI, including sensor robotics, including social computing, and along with HCI. And I hope this talk can hopefully attract some of you to think about this topic and potentially working towards this vision. Finally, I wanted to acknowledge all the students and staff and postdocs working on this together with me. Finally, if you have any questions, I will be happy to address them.
Shengdong, thank you very much for a very interesting and also thought-provoking talk about heads-up computing. And before we move on to questions, I should also thank SydCHI community and local ACM SydCHI chapter for advertising our talk. And this talk is in a way organized in partnership with them. So we have a few minutes for questions.
I saw Anusha raise your hand earlier. Do you want to ask a question? Or?
Yeah, I was waiting if anybody else want to ask a question, but I thought that, it's an amazing vision and very interesting applications. But even in some of the videos, we still see that when people walk around and when they see the information coming in, their daily life activities still get interrupted. It's hard not to stop to look at the message and so on. So what kind of vision you have in future to get these distractions out, or some sort of a way seamlessly integrate with the user activities?
Thank you, Anush. That's a very good question. Right? We do have this vision, but realizing that it has lots of challenges. Right? One thing here is that you can see that sometimes mobile phone maybe is a good design, right? Because sometimes you can put your mobile phone in your pocket. Then even the message come in, you don't have to immediately attend to it, right? That might be a good feature. That might be a good thing. But if you have glasses, if it always show up in front of you, it can be even more annoying if the message is not what you want, right? So I think that's definitely a need to design into the kind of the control of the center. So who and what time and is allowed to deliver information, right? In what ways? Currently, I think, the current devices, they don't make a user-friendly interface for user to control that, right? To configure, the right amount of information that can be delivered to you, it would probably take a very challenging task for average people to perform, right? But I think for heads-up computing, this topic is more important, and we need to design an easy to control, easy to manipulate kind of control center to manage what kind of information we allow and want it to be able to see at different situations. That's one thing. The second thing is that we should think about how can we display the information that's least conflict with our current activities. We talk about some of that, like redesigning information display. We're currently experimenting with different ways. Like, instead of all information delivered in the visual channel, can we use multimodal ways to deliver the information? Right? You can just think about a complex task where you have to maybe accomplish, let's say receiving an email or sending an email and things like that. Some of the information we receive can be offloaded to the other channels, while others maybe unavoidably you need a visual to check. But if you try to minimize that and redesign the experience, user will maybe having a much better overall experience as compared to what we have right now. So that again put a lot of emphasis on the design part, understanding. And third thing here is what we call utilize of AI, right? The nice thing about what we have here is the wearable device is that it now have the ability to better understand us, right? Because they see what we see, they hear what we hear, they even have some understanding of our movement. It is kind of freaky and kind of maybe undesirable if you talk about privacy concerns. But if you use it in the right way, they can really facilitate and manage the information based on understanding of the user's current status. If they notice that I'm in a meeting, and then if they understand the meeting is important, depending on the type of messages, those less important messages will just not appear, right? It will manage that. And then it will only show them while you're taking a break, while you're going to the bathroom, or you're taking a water break. So with this enhanced understanding of our status, it can much better manage in terms of what kind of information and when and how it delivered to us. This is the thing what we call is part of the essence of the resource-aware interaction that we want to propose. Yeah. So I hope that answers some of the question, but this is a challenging topic. It requires a lot of work, and I hope eventually we can come up with something that everybody will find it nice to use.
Absolutely, yeah, it's a very challenging problem indeed.
Yeah,
are there any more questions? I understand this is,
I
start
saw
of the semester, so a lot of people are busy teaching. Sorry.
Oh, I saw Barbara raised your hand earlier. Do you want to ask a question?
No, it was actually clapping.
Oh, okay, thank you.
Any other questions?
Just one quick question.
Sure.
So when you talk about human-centered device, human-centered and device-centered, so you mean like so currently humans trying to adjust to devices to like operate on for example, on smartphone. So I see what they are trying to do is basically change that to like head-mounted devices, and then basically like operates on fingertips or some device on that. So which means we are still have to adjust to that kind of gestures. I mean, like the operation systems, but actually different people have different ways of like habits. For example, someone would like just minimum amount of gesture. Someone might just like open a more wide operation space. So would that be a way to adjust the difference between the operating habits of human? I mean, just
Wenjun, that's a very good question. Thank you for asking that. I think there's two aspects to it. one aspect is the ability for you to be able to operating or interact with computers while you engaging other tasks. So our argument here is that yes, some people may not be familiar, or maybe even they don't even wear glasses. Some people don't like to wear a ring and all that kind of stuff. So it will maybe force them to, or maybe something undesirable for them to use, right? But what we're offering here is that with this platform, now you can say that maybe having a WeChat or WhatsApp chat with your friend while you are doing laundry, while you are cooking, right? So we offer you these capabilities now. Before, I mean, it's much more difficult. The device constrains you from doing that. So that's one aspect of that. The other thing is that we are still looking for more intuitive ways for you to do things, right? I mean, ultimately, ideally, this kind of things can be even more seamless. Actually, I think asking people to wear two devices is still a little bit difficult, perhaps. But I cannot think of any better ways at the moment.
Of course, with more
I think
advanced
all the technology here, they have this we call cost-effective ratio, right? If the advantages is outweigh a lot of the cost, then people just willing to do that. So right now, you cannot live without a phone, right, in your pocket.
Yeah,
a phone is also a burden, actually, right? But because it just offers so much benefit, you cannot live without it. With the heads-up computing, I can see that it can potentially offer more convenience than the phone. And with the great convenience we offer, hopefully more and more people will try to use it and find it easy to use. Yeah, but of course, if there are better ways to do that, let's moving towards that. Yeah, I fully support anything that can make it better. Yeah, thank you for the question.
Yeah, no problem. Thank you.
All right, any more questions? We probably can have one more question. If no more questions, I think it's time to thank Shengdong again. Thanks very much for your time and interesting talk, and hopefully you'll be able to visit us in person sometime soon. You're always welcome to come and visit the University of Sydney and give another talk in person.
Looking forward to it. Thank you very much.
And then thanks everyone for joining in, and we would like to see you all in our next bachelor seminar. Okay, bye-bye.
Bye.